And we're going to talk about uh, RL circuits, resistive inductive series circuits today. And pretty simple stuff. We're going to discuss fractional relations between resistance and inductive resistance and inductance in an AC circuit, series circuit. We're going to discuss the power factor, very important idea. And we're going to calculate all the voltage values, current values, all the values in the whole world, including the power factor. And we're going to use triangles to do this. Now, the textbook that you guys did homework out of, I understand it directed you and you did Pythagorean theorem. And I understand that. That's fine. Pythagorean theorem practice is fine. But that's not how we do it here. Because if you do something by Pythagorean theorem, and let's say you're calculating the impedance of a circuit, that's fine. You've calculated resistance, inductance, and impedance, but now you want to do a power triangle and you have no idea what angle you have for a phase angle. We'll talk about that in a few minutes. So it leaves you without the information you need to go to the next step. And I call this process simultaneous triangles, and we're going to do this later a lot. We're going to do this all semester long. So don't panic if you don't pick it up immediately, but it is the essence of this course. These triangles we're going to do today are the beginning steps, and then we're going to develop that into creating a second triangle, and we might even do a little bit of that today. So we're going to look at the simplest AC RL circuit in the world. We've got a resistor and we've got an inductor. An inductor is a winding, a coil. And remember, we've talked about the definitions that inductance is the resistive part of the total impedance. That's the result of AC going through a coil, the rising and falling that creates a magnetic field. And it's like a pogo stick in that you're jumping up and down, putting a lot of work into it, but you're not going anywhere, right? So inductive reactance is something that is not productive. It has a purpose. There are good things about it, but it's not doing any work. So let's assume that we have 120 volt AC, and we're going to assume we have 30 ohms of pure resistance, and we're going to have 40 ohms of X sub C, inductive reactance. And so one of the things I want you guys to do from now on, every time you do any kind of a problem, I want you to put this over every resistor, inductor, capacitor, whatever it might be, and one for the totals. Now we're going to say this is the totals: power total, voltage total, current total, and impedance total. Okay, so we can have, if we have a circuit that's got a bunch of parts, we can put PEIZ. Now if you were in first semester and you were studying circuits where it was DC, battery powered, and it was pure resistance, you'd only have resistance. It would be PEIR. But we're not in that world anymore. Now we're in the AC world. And even if there is DC power, there's still going to be inductance and reactance and things like that. So from now on, every time we do a circuit, we want to have the PEIZ, because we know that if we go from the top down, we divide. If we're going from the bottom up, we multiply. Okay, so what were those totals we had for resistance? Now, one of the things I've told you, I believe, is we always put the 90-degree angle off to the right. We always put our phase angle here. And we always put our resistance, when we do resistance, down at the bottom. That is the side adjacent of a triangle. And the side opposite the angle, is the X sub L, inductive reactance. And we had 40 ohms of that, didn't we? Isn't that correct? Okay. So now what we need to find is the Z, the impedance. Okay. Actually, I need to stop the recording for just a second. my board here is not calibrated and it's drawing things out of place. So I'm going to take a pause and we'll be right back after this message. Okay, so our Z, our impedance, is always the hypotenuse. Now we're going to have another triangle later. Every circuit in the world is going to have apparent power, true power, and reactive power. Okay? And also, if this is a series circuit, what is always constant? Current's constant, so we can't have a current triangle, can we? We can, but it's flat. It's a straight line. It's all the same, right? Not much of a triangle. But we could have a voltage triangle, couldn't we? Would we have a voltage triangle? Absolutely. Now, what would be the three sides on a voltage triangle? How about the total voltage, the voltage across the resistor, and the voltage across the inductor? How about that? Would that be okay? Okay, that's true. Anytime we have a series circuit, we have a voltage triangle also. Now, what do these three triangles have in common? Are they the same lengths? No. Are they the same anything? How about the angle? The angle is what we call the phase angle. And every circuit has a phase angle. And the relationship between the inductance and the resistance will set that angle. And because of that, the electrical efficiency of this thing will be decided. That relationship, the cosine of this angle, is called the power factor. And when we, oh, that was clever. No. So the cosine of this phase angle is called the power factor, and it tells you, and that's because it tells you how much of the incoming apparent power is going to be converted to true power, in other words, real work. So how much real work the circuit is doing. Now, I'm not including friction, heat, things like that. Just the pure electrical efficiency all by itself is known as power factor. Very important thing, because a motor can't be more efficient than its power factor, but it can be less efficient than the power factor, right? Okay, so we want to have a fairly efficient motor. Now let's go to my next slide, if I have one. No, that's right, we were going to do this circuit. We had 30 ohms here, and we had 40 ohms in the X sub L. And now we go back to our triangle fundamentals, and we look at this, and we know a couple things. We remember that sine, cosine, and tangent are oh hell, another hour of agony. The sine is oh hell. The cosine of the angle is another hour. And the tangent is of agony. Sounds like homework, doesn't it? Oh hell, another hour of agony. So that should be easy to remember. Oh hell, another hour of agony is sine, cosine, tangent. Or if you want to make it SOHCAHTOA, it's my old Indian friend Sokotoa. You can envision him putting his toe in the water and going, my God, that water's cold. So we're going to remember sine, cosine, tangent. Now, looking at that, and we have the side opposite and the side adjacent, the opposite and the adjacent, what function do we have right now? Tangent, that's correct. Very good. So, if we have the tangent, and we had a handy-dandy TI-30X2S calculator, we could pull that baby out and say to our calculator, what angle has this tangent? Let's pause while we pull out our TI-30X2S. All right. Now, I know that you already know how to do this because we've talked about it before, but let's go through this one step at a time. Pull out your TI-30X2S and hit clear twice. We get all the junk out of the memory. And we're going to put in second function. In other words, tell me what angle has this tangent. So second function tangent. And then we're going to just put in, the tangent is the opposite, so we're going to put in 40 divided by 30. We might want to put it in a right parentheses, but we don't have to. But go ahead and do that. Right parentheses and enter. And it tells you 53.1301 degrees. Actually, the number keeps going out, right? So now leave it in there. Don't touch it yet because we want to find something else out, right? We want to find the hypotenuse. The hypotenuse is the impedance of the circuit. So what we're going to do now is we've got the angle in there, right? So now we're going to hit cosine, second function, answer, and that will find the cosine of that long exact angle. So we're going to find the cosine, and the cosine of this angle is what? Say again? 0.6000. Okay. Now, I want to tell you now, or remind you, that the cosine of the angle is the power factor. That means this is a decimal, and if we want to turn a decimal into a percentage, we just multiply it by 100, right? So 0.6 as a decimal turned into percentage would be 60%, right? So this circuit is turning 60% of its apparent power into true power. Is that satisfactory? That's not a very satisfactory situation. We don't like that. And we're going to discuss later how we can change that, because we can. All right? Now, if we know the cosine is 60, now let's look at our formula over here for cosine. And we're going to start plugging some things in. And we're going to plug in that the cosine is 0.6000. And that's equal to A, which we know the adjacent is 30, over the hypotenuse. So if we know that, we can look at this and say, wait a minute, I know that thing about A is equal to B over C, and I can switch A and C automatically. Or I can multiply both sides by A and divide both sides by C, and I'll wind up with C is equal to B over A. What does all that mean? That means that we can take H and exchange it for the 0.6, and we still have the same formula. So now we have H, the hypotenuse, is equal to 30 divided by 0.6. And if we take, now what's in our calculator right now? 0.6, right? Well, that's not exactly what we want. But remember, our handy-dandy TI-30 remembers our last answer. So we're just going to punch in 30 divided by second function, answer, and we find that H is equal to what? Say again? 50? Okay. And what do you think that is? That's our impedance. That's our Z. So we know that the total impedance, the total resistance to AC flow is 50 ohms. So now we've said that we have 120 volts. And we've also said now that we have 50 ohms of total impedance. Now we have 50 in our calculator at the moment, don't we? Now we know that we want to go from 120 down to I. We want to get our circuit current, don't we? Okay, so we've got 50 in our calculator, so we're just going to put in 120 divided by second function, answer, enter, and then we find that our total current is, thank you, 2.4 amps. Wow! And then if we want to multiply up, we could get our total power, right? 2.4 times 120, we could. We're not going to do that just now because there's other things we want to find out. Oh, wait a minute. That is something else we want to find out. What's in our calculator right now? 2.4. Now hit times 120 equals, say again, 288. Now is that watts? No. Hook up. Nope, that's volt amps. That's VA. Apparent power is measured in VAs, volt amps. What you have coming into the circuit is apparent power. And this is our apparent power. Coming into this circuit, we know we have 120 volts. We know it's flowing 2.4 amps. We can read those with a meter. So we can find our apparent power. Can we read our true power? With what? A watt meter. We could. A watt meter measures the resistance, measures the current and the voltage, and somehow it figures out how much real power is flowing through it. And we've got a couple of those in the lab, so, oh, that's a lab project all by itself, operating a watt meter. Oh, cool. Okay, so now we're going to have a new triangle, right? Let's get rid of something. Let's get rid of all of this in here. Isn't that cool? Okay, so now let's start a new triangle, and we have 288 VAs. Everybody agree with that? Don't we know this angle? What was our angle from before? Point. So we still have our old angle, right? 53.1301 degrees, and we have the hypotenuse. We'd kind of like to know the apparent power, right? That is the apparent power, 288 VAs. We'd kind of like to know our true power, and maybe we want to know how many VAs we're spending on creating and collapsing the magnetic field, sometimes known as VARs, volt amps reactive. That's what we call the reactive power. So down here, the result of the resistance is true power. And over here, we have reactive power. Okay. Now, we could just say that we know that the power factor is 0.6, and we could multiply that times 288. That would give us our true power. But we're not going to do that this time. What we're going to do is we're going to say that we have the cosine, and that's equal to A over H. Okay, let's plug in some things we know already. The cosine is 0.6, and that's equal to A over H. H is something we're looking for, right? No, H is what we have. H is the hypotenuse, 288. We're looking for the side adjacent, which is true power, right? So now we have the cosine is equal to A over H, except we have solid numbers for everything except for the thing we're looking for. Isn't that wonderful? So now we can just multiply 288 times both sides, and we'll get down here 288 times 0.6 is equal to 172.8 watts. That's how much power this circuit is creating. Okay? Because of the relationship between the coil impedance, coil X sub L portion compared to the resistance of the coil. Now, let's find, how do you think we could find our total reactive power? We might need to use our sine, right? Let's look at the sine of theta, and that's equal to O over H, right? Okay, let's plug some numbers into this. We know that our angle is 53.1301. We're finally going to have to hit clear. Hit clear. And hit sine, and then put in 53.1301 and hit enter. We get a number. And that's the sine of this angle. That's the relationship between the opposite side and the hypotenuse. What is that number? .7999999. Okay, let's call that 0.8. Just for the S's and G's. And that's equal to the opposite. Do we know the opposite? No, that's what we're looking for, right? We're looking for the side opposite, which is the reactive power, right? And we know the hypotenuse, though. What is the hypotenuse? 288. Well, there we go again. We've got 288 on both sides, and it's divided over here, and we could get rid of it by just saying reactive power is equal to 0.8 times 288, and if we multiply O over 288 times 288, 288 will drop out, so we get side O. So 0.8 times 288 is what? .230 what? 4 VARs. Volt amps reactive. Let's get rid of some of this stuff. And we don't need that anymore. Or any of this. Okay. What was it? 230.4. 230.4 bars. All right. So now we've found out everything about this circuit, haven't we? Except how to change this. And if we know the VARs, we know how much we want to change this. So that's why we want to know that part. So let's look at some things we know. Okay, in a pure resistive circuit, the voltage and current are in phase with each other. In a pure resistive circuit, only in a purely resistive circuit. Is any circuit ever purely resistive? Not really. There's always a little bit of inductance or capacitance or something. In a pure inductive circuit, the voltage and current are 90 degrees out of phase. Is there ever such a thing as a purely inductive circuit? Not exactly. Close, but not exactly. In an RL series circuit, the voltage and the current will be out of phase somewhere between 0 and 90 because purely resistive is 0 degrees out of phase and purely inductive is going to be 90 degrees out of phase. So it's going to be someplace in between, right? So anytime there's an inductor and a resistor, and anytime we wind a coil, it's going to have resistance and it's going to have inductance. Pure DC resistance and inductance. So a transformer, a motor, any place there are windings, this is going to happen. In other words, everywhere in electrical. Everywhere. It happens everywhere. Okay, so total circuit values include total voltage, total current, total resistance, total power, and which is apparent power and true power. Now you have been told in DC the first semester that power is always additive. Okay, that's sort of true, and it's mostly true, but not necessarily true. True power is always additive. Apparent power, not always. Okay, so remember, the thing that you found easily in the first semester was apparent power, but that doesn't add up perfectly every time. So let's see one other thing we know here. What else do we know? Pure resistive values include voltage drops across the resistors. Oh, we didn't do the voltage triangle, did we? But we would have done it the same exact way as we did the power triangle. And just so you know, in this class, we're going to do the power triangle more often than we're going to do the voltage triangle. Okay, we are going to do both, but we want to know, we can see and measure certain things. The voltage drop across the resistance, we could read that. The voltage drop across the coil, we can kind of see that. Not exactly, but sort of. We can infer what it is. Okay, pure inductive values, I'm not even going to worry about that. Angle theta, that's always that angle between the hypotenuse and the side adjacent. It's always that angle, okay? And we're always going to draw it with a resistance across the bottom and the X sub L going up. And if we have an X sub L, it's going to go from, let's not talk about that just yet. I don't want to confuse you. Okay, and the cosine of the angle is equal to the power factor. Cosine of the angle tells you how much apparent power is going to be converted into true power. Very important factor. And power factor is equal to the relationship between VAs and watts. Okay, vectors, we know what that is. That's the lines. When we create the hypotenuse, that's a vector because it's got distance and force, right? Okay. And I'm going to stop now, and we're going to figure out what we're going to talk about next.